Now we'll look at two examples of determining limits of functions of two variables. Here we have the limit as x comma y approaches 2 comma 1 of x plus 2y squared. For a quick review, as x comma y approaches the point a comma b, the limit of f of x comma y is the value L if the limit from all paths approaching the point a comma b exist and are equal to L. So let's assume the graph of this surface here is our function f of x comma y. This limit equals L because as we approach the point a comma b from all these paths, notice how the function value is approaching the same value, which would be L. Of course, this doesn't illustrate all the possible paths. Notice how there are potentially an infinite number of paths to consider. However, if our function is continuous over a region containing the point a comma b, we can find these types of limits using direct substitution. So going back to our example, notice how our function f of x comma y equals x plus 2y squared is continuous over all real numbers x comma y, and therefore we can find this limit performing direct substitution. It's also helpful to graph the surface if you have three-dimensional graphing software available. I provided the graph of our function here, and notice how the surface is continuous everywhere. So to find this limit, we can simply substitute 2 for x and 1 for y. We don't have to consider various paths shown here that approach the point 2 comma 1. So our limit is equal to 2 plus 2 times 1 squared, which is 4. Let's look at a second example. Here we have the limit as x comma y approaches 2 comma 1 of our rational function here. Notice when x is 2 and y is 1, our function is continuous, which means once again we can perform direct substitution to find this limit. For example, notice how at the point 0 comma 0, we'd have the indeterminate form of 0 divided by 0, so we would have to consider various paths approaching the origin if this was approaching 0 comma 0. But because it's approaching 2 comma 1 and the function is continuous at that point, we can assume there's a region where the function is continuous that contains this point, so we can find the limit performing direct substitution. So we would have 2 squared times 1 in the numerator divided by the quantity 2 squared plus 5 times 1 squared. So simplifying, we have 4 divided by 4 plus 5 or 9. So here the limit equals 4/9. So if you're looking for examples of limits of functions of two variables where we consider paths to determine the limit or if they exist, I do have other examples that require this. I hope you found this helpful.